In this video, we want to look at doing vector projections with some real-world examples. So this example is that we have a sled and cargo that weighs a total of 200 pounds, and it's on an incline. And this incline, okay, this is totally not to scale. This incline is at 25 degrees. So we've got, a sled right here, and the total weight is 200 pounds. But we're going to look at this as a vector because we know that if I were to do this as a vector, the force of the gravity is where this comes from. So this is 200. Now, it's 200 pounds, but if we look at this as a vector, I need to scoot this over a little bit so I have room. We would actually describe this as negative 200 J because it's going straight down, so it's only in a vertical direction, so that's why it has the J component. And it's negative 200 because that's the direction that we're pulling is going down negative 200. So the question that we have here is trying to figure out what is the minimum force required to keep it from sliding down this incline. Now, we've seen this in different places before, how we can break it down and use sine, use other trigonometric functions to figure out what the different components are of this vector breakdown. But what we want to do here is with the dot product, we want to look at the vector projection. So I'll be honest, the first time I was looking at this, I'm still going like, what do you mean? We're trying to figure out what is the force that I have to apply here to counteract the force of this guy sliding down, right? I need to counteract that. Well, here's what we're going to do. We're going to call this guy just vector W. And really it's just going to be some kind of generic, and we can even say that this is a unit vector, right? I don't know how big it has to be. Just call it a unit vector. What we're going to do though is that with this, with a vector projection, we'll be able to figure out what this piece is right here, and that's going to match up with what this piece is right here to keep it from sliding down. Again, it's you got to make sure that you're paying attention to direction, all this other stuff. All right, so let's see what we have. So if I were to do that, that vector projection, I am going to do this. Let's see. I want to take the vector projection of my gravity, and I want to do it onto W. So the way that we do that is by doing Fg dot W over the magnitude of W squared, and then times vector W. Again, what I mentioned in the previous video is that all of this stuff right here, this guy is just some number. So we just need to figure out what are we going to multiply that vector W by. Now you might say, well, what is vector W? We know that it's going to be going in this direction, but what is it? Well, we know that vector W can be broken down into its two components, into its x and its y, right? So again, we're calling this the unit vector, right? So it has a magnitude of 1. So this guy's just going to be cosine of 25 degrees I plus sine of 25 degrees J. And so we're going to put that into this formula and see what we come up with. Now, I'm afraid I may run out of room, so please bear with me. So if I'm going to do Fg dot W, I'm doing the dot product between this guy and this guy, right? So remember, Fg is just negative 200J. So if you wanted to, you could see this with I and J, but the I value, or the I unit vector, is going to have a coefficient of 0. So when I do the dot product of the I parts, it's just going to be 0. Leaving me with the dot product between, with the product here, so it's going to be negative 200 times the sine of 25 degrees. All over. Now, here's a bit of a trick. We have kind of made the declaration here that this guy is going to be a unit vector. In fact, when I had all of this, I'm really just multiplying times an understood 1 because I just want to know the direction for W so that when I do my vector projection onto it, it's going to be going in the correct direction. It's going to be parallel to that, right? Well, if this is a unit vector, that means the magnitude of W is just 1, and when you square 1, you get 1. Right? And even if you didn't see that and said, oh, but I've got to do this, I got to do this a long way. Well, you would have this. You would have to do the square root squared, and inside you would have cosine squared of 25 degrees plus sine squared of 25 degrees. Oh, that's a Pythagorean identity. Cosine squared plus sine squared is just equal to 1. Square root of that, and then squared, still just going to give you 1. So we don't really gain anything by doing that. So we need to recognize that we are just, starting with some kind of default vector that we want to be parallel to. Call it the unit vector. Make your life easy. And then this is times vector W. Man, I do not have room for this. All right, so I'm going to have to scroll down a little bit so I can actually write all this out. So I apologize for the messiness. You're going to be fine. So we have negative 200 sine of 25 degrees times cosine of 25 degrees I plus sine of 25 degrees J. And when we work this out, we'll be able to figure out what is that minimum force required. Well, keep in mind that minimum force, right, is going to be the magnitude. And so it's going to be the magnitude of this guy right here, right? Because this is going to give you the directional piece, right? But this value out in front is going to be the magnitude, right? So one of the ways we had of talking about vectors before is that we could say, here is vector u, and it's equal to the magnitude of u times cosine of theta I plus sine of theta j. And so you see the direct line up here, and that this guy right here is supposed to, be my magnitude, right? All right, so let's go to the calculator and see what it tells me. So with my calculator, I got to change my mode because now I'm talking about degrees. So I would do negative 200 sine of 25 degrees. So this guy right here is that vector projection of V onto W. So this is equal to about, this is about negative 84.5. Well, I'm just going to keep this as vector W, right? So in my picture, this force right here is the negative 84.5 pounds. So the question is, what's the minimum force exerted to keep it from sliding down? Well, that means we're going to have to provide a force that is positive 84.5 pounds. It's going to be in that particular direction to counteract the sled from sliding down. Okay? All right, well, let's look at one last problem here dealing with work. So in physics, work is going to be the product of the force times your distance. All right, and so when we're doing it with vectors, it really becomes a dot product, and it's going to tell us what our overall work is. So a lot of times the units that we have for work is going to be in foot-pounds or Newton meters or joules. But here in this problem, we're going to be talking about foot-pounds. All right, so here's the situation. We've got a wagon. Just pretend that's a wagon. And it's being pulled with a force of 40 pounds at an angle of 20 degrees. And we want to know how much work is done to move this wagon 320 feet. So you really have the force, which is in pounds, times the distance, which is feet, which is how we're coming up with the units foot-pounds, right? And so what we want to do is we want to, do your vector projection stuff. But this one's pretty simple because you've got your distance here. Your distance is just going to be the vector 320i. There's no j because you're not moving up or down, right? And this horizontal force, or that projection, is really just going to be 40 times cosine of 20 degrees I. Now, we could kind of, forget I even said that and just say, what is my force fully as a vector, right? And so that force would be 40 pounds times cosine of 20 degrees I plus sine of 20 degrees j. Okay? Let's say that, right? Well, that means that my work is going to be force times distance, force dot distance, to the dot product here. My force, if we were to distribute this, is going to be 40 cosine of 20 degrees I plus 40 sine of 20 degrees j dot 320i. Well, if I do the dot product here, I would multiply the I pieces together. So that's going to be 40 cosine of 20 degrees times 320. Then you multiply the j pieces together. So that's 40 sine of 20, but the j piece for the distance is going to be 0. So that piece goes away. And all we're left with is this guy right here, 40 cosine 20 times 320. Let's check the mode again. I am in degrees, so that works out nicely. I'm just going to do the 320 first. 320 times 40 cosine of 20 degrees. Let's see, the total work done is going to be 12,028 foot-pounds. So it's that force, and of course that the horizontal component of that force was 40 cosine 20. So pulling with a force of 40 pounds, but in terms of the horizontal, it's 37.6-ish pounds, times 320 feet. So this is how much work has been done by pulling that wagon 320 meters. So break things down in terms of the vectors, in terms of the I and the j, do the dot product, and you got it. And you see that some things, like that vertical force, doesn't get calculated into the work, because when you do the dot product, there's just a 0 right here. So too bad, so sad for that.